All right. Hey folks, Emily here. In this video, you are going to learn how to build your own high-performance kernels on AWS Trainium. Let's dive in. All right, so we come to the compiler. So remember, you develop your models in PyTorch. You use your NeuronX distributed APIs to distribute your models. You use maybe PyTorch XLA to compile that model down to enter what's called the Neuron compiler. And so the Neuron compiler fundamentally is the intermediary between the driver and the neuron runtime and the low-level execution on the device. The compiler is the intermediary between that and your PyTorch frameworks, your applications, NXDT and NXDI. So let's try to understand the compiler. So the compiler fundamentally is trying to do a couple things. Number one, it's trying to improve the performance of your model, actually. So we study automatically through the compiler. We study the graph that is your neural network, that is your model. We try to optimize the loops of that. So we improve the layout by reshaping the matrices, reshaping the tensors. We establish tiling protocols to better optimize through your loops. We'll try to vectorize your data movement. We'll try to pipeline the compute so that it's nicely overlapped. And then after that second phase, we move into the third phase. It's called hardware intrinsic mapping. Hardware intrinsic mapping means we look at the sort of optimized loop that we defined in that second phase of the compiler and then map the key operations from that into the instruction set architecture. And the instruction set architecture are the core capabilities and the core functions that are possible through the hardware natively. And so that hardware intrinsic mapping stage is essentially the mapper between the math that you defined in your model. After the graph was optimized and the loop was optimized, then we map the operations from your math to the hardware directly. And then that fourth stage is scheduling and allocation. And this is where we take the entire set of hardware instructions you intend to run, which you define through your model, and we schedule them. We figure out precisely which operations are executed at each moment in time across the entire chipset and the entire neuron core. So the neuron compiler does all four of these key phases for you. This is why we use PyTorch XLA, and this is why we use NeuronX distributed to define your model, send it to the compiler, and then the compiler generates that NEF artifact, which we then send to runtime for ultimate execution. So that's the Neuron compiler. Now, a kernel. So a kernel fundamentally is a set of user-defined instructions that essentially bypass a compiler. Most of the operations in your model are not kernels, right? Most of the operations in your model are sent through the stages of the compiler. So you accept the compiler's decisions for the graph optimization, for the loop optimization, which means the layout of your tensors, the tiling through your tensors, the vectorization, that hardware intrinsic mapping, and then eventually the scheduling and allocation. Most of the operations in your model, you're just going to accept those directly from the compiler. Why? Because it's so much more efficient to just use the instructions and use the layout decisions made through the compiler. It's faster for you, it's faster for your program. However, when you are studying the performance of your model, when you're looking at that roofline model, when you're identifying work that is extra that you want to remove, or you are identifying the extra cycles that you want to consume, so either of those key phases, you're going to find bottlenecks. And some of the bottlenecks you're going to be able to address at a higher level. Like maybe you can change the hyperparameters of the model by increasing the number of batch records, for example, on inference or training. Or maybe you can change the sharding layout of the model, such as modifying the tensor parallel degree. Maybe you can change the size of shapes that you're sending to the compiler. So you'll compile for a target sequence length or a target max context length, and then use what's called bucketing for all of the intermediary stages in between. So there are some higher level ways that you can improve performance. But fundamentally, a kernel is the lowest way for you to optimize performance on the hardware just directly. And so kernels are a way for you to identify performance bottlenecks and then address the performance bottleneck by developing your own algorithm that is built for a hardware set to improve and then optimize performance of your models. Really, kernels are what it's all about. Like, kernels are how you get good performance on your language models. Kernels are what makes your language inferencing faster. Kernels are what makes your training jobs faster and more efficient. Kernels are how you get better utilization. Kernels are how you get better memory utilization. And it's not the case that when you write a kernel, you get better performance out of the box. That's not the case, because there are many different stages of kernel development. You might start with something that we see here, which is a softmax. It's like a hello world kernel. It's where you're just learning how to write the language, you're learning how the syntax works, you're learning how to use some of the APIs that are relevant. So that's just, say, like a hello world kernel. But as you spend time studying the performance, as you spend time learning about the hardware, figuring out how you can better optimize your utilization, you're going to develop a kernel that addresses those compute performance bottlenecks in the context of models and operations and workloads that you care about. And that is where your compute kernel is going to give you the ultimate performance on a given hardware set. So you can develop your own kernels on Trainium today with NKI, or the Neuron Kernel Interface. So NKI gives you the best of both worlds. NKI combines higher level programming paradigms such as Python, such as NumPy, such as PyTorch, and then actually enables low-level access through the ISA library. So NKI is the kernel interface for Trainium. NKI is how you can define your own algorithms and your own kernels that enter the compiler at that lowest level, essentially. So NKI is a part of the compiler. When you're writing a NKI kernel, it looks like Python. The syntax is designed to be very compatible with Python, but you're actually controlling the compiler in the backend to get that low-level bare metal access, but do it in a way that's fast to write and fast to debug, because the interface is actually Python. It's a Pythonic interface with bare metal programming access to Trainium chips and Trainium accelerators. So NKI exists as a vehicle for you to accelerate your own algorithms with the NeuronCore. Remember, the NeuronCore is the heart of the acceleration. The NeuronCore fundamentally is what enables you to develop algorithms that move data really quickly to optimize performance for your workloads. And that NeuronCore is what you see on the left-hand side. This is the NeuronCore V2, and it is the same NeuronCore within the Trainium 1 instances and the Inferentia 2 instances. So both the instances and the chip have the same name, Trainium 1, Inferentia 2. Those use the NeuronCore V2, and that is what you see here on the left-hand side. So remember, we looked at the Trainium chip, and we saw we had those 4 HBM banks, and we had 2 dies of raw silicon, and we wanted to move our data quickly on that raw silicon. This is the same HBM bank. We're just seeing it here in a slightly different way. Once we've moved data from the CPU down the PCIe bus onto those HBM banks, the next place we're going to land it is onto SBUF, for the state buffer. SBUF is our on-chip memory cache, and SBUF is a local memory scratch pad, essentially, that you can manage through NKI. So when you're developing a NKI kernel, the core job you're taking on is managing that on-chip memory cache. You're managing the data that's being moved from HBM down what are called the partition lanes. So we have these 128 partition lanes you'll come to learn all about. So we're going to move data from HBM down those 128 partition lanes onto SBUF. Once we've landed the data onto SBUF, we have 4 compute engines that you can utilize to optimize performance. The tensor engine is a systolic array architecture that enables incredibly performant and efficient matrix multiplication. So when you're doing a matrix multiplication, you're going to, again, move your data from HBM to SBUF. You're going to land it on the tensor engine to do the matrix multiplication, and you're going to accumulate the results in this secondary on-chip memory cache, which is called PSUM. PSUM is similar to SBUF, but in terms of its ability to move data, but it's different in size. PSUM is designed to be much smaller so that it's simply storing the residuals. So you move in your kernel, your first step is defining your tensors, and then you move your tensors from HBM to SBUF. The command is called nl.load, and we can actually just have that pop up here. So nl.load. So the command is nl.load. With nl.load, we're actually physically moving the tensor that you defined in your program from HBM to SBUF, and we move the data down. Once it's on to SBUF, we want to, again, define the computation. We want to use the available engines to accomplish the mathematics that you've scoped in your algorithm. The way you're going to do that is using one of two language constructs that are available in Niki, Niki.language and Niki.isa. Niki language is a higher level, sort of easier framework that you can use, where the syntax is closer to NumPy and it's closer to open source programming languages for acceleration. So we land our data on SBUF, we move it onto the various engines, we accumulate the results of those computations into PSUM, which is that secondary on-chip memory cache, and then we're going to move data back from PSUM into two engines, into either the vector engine or the scalar engine. These land back on SBUF, and then we're going to load them back onto HBM, so move them back up with nl.store. And together, that is the core, those are the core components of a kernel, really, is moving data, is designing the tensors, designing the layout of your algorithm, and then the layout of the data for your algorithm, moving that down, so managing the data movement through the partition lanes onto SBUF, mapping the computation for your algorithm to the various engines, managing how you are moving through your tensors, such as through tiling, in order to optimally send data to the various engines, accomplish the execution, store the results in PSUM, and then send everything back to HBM. On the right-hand side, you can see the hierarchical memory capacity and bandwidth that's available as you move through these various stages. So remember, on HBM, you get a pretty reasonable clip of data movement, but then that jumps up dramatically when you move on to SBUF. So the reason why you want to write a kernel is because you can move data on SBUF 20 times faster than you can do so on HBM. So the heart of the kernel game, the kernel puzzle, is figuring out how you can do that most efficiently within the context of your workload. There are two ways to write Niki kernels, language and ISA. Niki language is a set of APIs that includes memory operations, again, so you can move data and manage your memory, your on-chip memory and HBM. Creation operations such as defining tensors, the mathematical operations, so you can define the mathematics for your algorithm, and we will map those to the engines on your behalf in the case of Niki.language, and the rest of a whole set of capabilities that enable you to, again, write kernels, both like hello world, getting started kernels, and then the high performance ones that will move the needle in your applications. The second way to write a Niki kernel is with the ISA, or the instruction set architecture. So we make the Neuron instruction set architecture for Trainium, we make that available through Niki, actually. So you can read the available instruction set architecture through Niki and design algorithms that use the available instruction set. And our documentation for Niki is excellent. You can read all about the programming paradigm. You can read all about the memory options, the compute options, the available raw hardware specs, and then again, using the profiler to study the performance of this. And the ISA is a really important way for you to improve the performance of your kernels. We have many Nicky kernels that are available off the shelf. So you can import Nicky kernels through a variety of ways. You can import them through the higher level libraries, so NeuronX Distributed Training and NeuronX Distributed Inference. Both of these manage the invocation of kernels on your behalf. You can also import them directly from the compiler, actually. So when you install the NeuronX compiler, that includes Nicky as a part of it. That means you can import the production Nicky kernels by default and add them to the rest of your PyTorch projects. So we have many kernels that are available off the shelf, again, for FlashAttention, forward and backward pass, in addition to collectives, token generation, blockwise, mixture of expert kernels, stable diffusion, allocated stable diffusion, etc. You have many kernels, again, that you can import directly or that you can study because they're available on our GitHub repositories. So definitely encourage you to spend some time studying these, learning about them, and then writing your own kernels as well. With that, let's take a look at the demo.
Today we're going to show you how to write a simple Nicky kernel and how you can write custom kernel-based operations against Neuron hardware. To get started, I've got a VS Code environment on a TRN1 2x large instance. If you're curious on how to set up a development environment for working with Neuron, we've got a previous video you can refer to check out. As I just mentioned, this is a TRN1 2x large. This means that on this instance, we have one Trainium device, and that Trainium device has two NeuronCore cores available. We can quickly check out those Neuron cores with Neuron LS just to validate everything looks good. So here we've got our instance type. It's a TRN1 2x large, as just mentioned, the instance ID. And then here we can see we have one Neuron device, our Neuron device 0, two Neuron cores, and 32 gigs of memory. So we're ready to get started. The kernel we're going to walk through today is a simple tiled matrix multiplication kernel. Here we're going to show you how you can use Nicky to perform a matrix multiplication of two matrices, matrix A, which is 64 by 128, and matrix B, 128 by 512. So let's walk through the code of our kernel. First, we define a kernel function, and we add this Nicky JIT decorator at the top. This tells our compiler that this function is going to be a kernel written in Nicky. The first thing we do is we set up an array. We use this Nicky language API to set up an n-dimensional array. The result of this operation is going to be 64 by 512, so we set those dimensions, we set our associated D type, and then we also say where we're going to initialize this, in this case our high bandwidth memory. The next is we need to set indexes. So we need to have an index to determine how we're actually going to read these matrices from our memory into our state buffer and then load into our tensor engine. So we set up these grids which represent the index for the left-hand side, the right-hand side, and our output. And then this is really where the magic happens. We have this nlload command which is actually going to load our input matrices from our high bandwidth memory to our state buffer, or HBM to SBUF. Here, we call this our left-hand side tile because we're using that previously defined index to tile our inputs for the left-hand side and right-hand side. And then, once we load these, we multiply these tiles together using this nlmatmul command. So here, Nicky is going to feed these tiles through our tensor engine, multiply them together, and write the result out to our partial sum buffer. Next, we copy from our partial sum buffer back into SBUF so that we can write back to HBM. And lastly, we restore our results in HBM. So we've walked through the kernel source code. Now let's actually run it. So here we initialize two random tensors just for the sake of this demonstration. We've got our A transpose tensor. We're actually transposing it to make it a little bit easier to work with our indexes. So it's 128 by 64. We have our B tensor, which is 128 by 512. And here we feed these to our kernel, and we're going to print the result out. So let's run this real quick. So this should take a moment. It's going to compile in the background, and then we'll run our kernel, and we should see our results come out. And there we have it. Because of the shapes and kind of the fact that we're using a normally distributed distribution for our random matrices, we get this matrix out the other side, and we can see it's of the proper shape, 64 by 512. This is awesome. We've been able to write and run a matrix multiplication all in our kernel library on a Neuron device entirely from scratch. Now this is super cool, but there are a few other features in Nicky that are pretty awesome that I want to show you. One is that oftentimes when we're writing kernels, we're doing so to achieve best-in-class performance on the hardware that we have available to us. And in doing so, we often want to produce benchmarks and profile our kernels. Nicky gives you a great and easy way to do that. If you remember, we added this Nicky JIT decorator at the top. Now we can replace this decorator with the Nicky benchmark decorator. And this will take in two arguments. One is the warm-up steps that we're going to use. We're going to use 10 warm-up steps and 100 iterations. So we'll save and we'll run this real quick. While this is running, our kernel is being stood up. We're invoking it 100 times, and we're saving the results to produce a helpful little benchmarking report that can give us an understanding of the performance. And here we have various metrics about performance. We can see that the NeuronCore latency that we're running against, we're seeing 18 microseconds. So it's pretty stable in our latency. Our P1, P50, and P99 are all consistent. Maybe that's helpful in understanding the various ways the kernel latency might change over time. For profiling, we can do the same. We can replace that same decorator with the Nicky profile decorator, and it will save our NEF file and our NTFF file that we can then import into the Neuron Profiler. If you're interested in learning more about the profiler, we have another video that you might have watched already that details information about how to use the profiler and how to get some performance insights regarding operations on Neuron. Thanks.
All right, so thank you, John, for the matrix multiplication. I loved getting to see the profiler and understanding the performance of that kernel. So a couple calls to action here. So the easiest way, again, to work with Nicky kernels is just to use the ones that are already built. Again, you can import them from the compiler, you can download them from our GitHub repository, you can add them to your models and start to see performance improvements. When you're writing your own kernel, when you're taking that on as a goal, the best thing you can do for yourself is just start really small. Understand the shapes of the workload that you want to optimize. So the size of the tensors that you want to move and that you want to accelerate, understand those, and then just start with the smallest possible ones. Start with things that fit really nicely on SBUF right away, and define the numerical verification for that, or achieve rather numerical verification for that small kernel just as your first phase. And then you can start to increase the size of those shapes, such as by tiling and iterating over the larger space of your model. You can add those kernels into your PyTorch models while you're testing and developing. Then again, you can use the profiler to identify performance bottlenecks. All right, and then again, a big thank you to the team. There are so many, amazing Amazonians who worked really hard to make kernels, Nicky, the compiler, Trainium available for you today, and we wouldn't be here without them. So with that, thanks.